Awesome. So
Okay, I
take it
started
away.
this. Okay, thank you. So hello everybody. Hello everybody. My name is Roman Baranowski. I am a member of UBC ARC team, and I am with ARC since the inception for the last 10 years, and I am working within the HPC environment for the last 20 something years. I hope that this will be interesting introduction to HPC environment. How does it work? What are the best practices? How to deal with this basically kind of a beast. So before I define what is really HPC and high performance computing and also high throughput computing, let me first give you the landscape, what we have currently within the UBC and within Canada. So at UBC, we are operating a computational platform and storage platform. It's accessible for everybody who is basically doing research within the UBC. And in addition to our internal resources, Chinook and Sockeye. Chinook is a storage platform and Sockeye is a computational platform. Of course, we have also a part, we are collaborating and we are the members of the Digital Research Alliance of Canada, which basically operates multiple sites and multiple systems across Canada. In BC, we have the Arbutus Cloud, and also a very nice and big computational system at Simon Fraser University called FIR. Then we have systems in Ontario, we have systems in Quebec, we have systems in Atlantic Canada. The only difference between accessing UBC systems and Alliance systems is basically that in terms of UBC, we are totally tied up with campus-wide login. So in order to have an account, you have to have valid campus-wide login, and your sponsor, your PI, your supervisor of your thesis, the person you're working with, basically she or he applies for the account and then sponsors your account. Within Alliance is operating slightly different identity management, but the process is very similar. Basically, PI applies first, and then everybody else within his or her group can join the project and have access to the systems. In all cases, we are using also multi-factor authentication, so it's a little bit complicated initially, but after that, it should be quite easy. Unfortunately, we are living in the era when the security multi-factor is basically starting to be mandatory. So right now, where do we start? As far as UBC ARC is concerned, the best way to basically is to visit our webpage and look at our documentation. There is a beautiful resource also available to UBC, provided by UBC Library. As far as the national systems are concerned, once again, there are documentation and there are web page of the Alliance. So that's where you start looking what interests you, where you would like to go, what systems you would like to use. And of course, if you have any questions, there is a support channel separate for the Compute Canada, sorry, for the Alliance and separate for us. But since we are working together, depending where you are posting your message, we will respond either through Alliance channel or our internal ARC channel. So right now, what is basically the kind of the architectural design within HPC and HTC architecture? So in essence, this is a system comprised of many computational nodes. In addition to this computational pure CPU-based nodes, we have specialized compute nodes which are equipped with multiple GPU units. We have nodes which have much more memory per core than the ordinary compute nodes. Uh, there is a quite substantial amount of storage connected to this. There are specialized nodes for the data transfer. So whenever you are moving data around, you're uploading, or you are moving data around for the further analysis or storage, there is a specialized data transfer node which are tuned up for the network connectivity and throughput. And of course, there are login nodes which have login in, and you are starting to interact with the system. In essence, this is like a collection of your laptops. But what differentiated these systems from your laptop or your desktop is basically very fast interconnect. All these computational nodes, all these computational resources, storage, data transfer node, they are connected via very efficient, fast interconnect, which means that when you are computing, you can basically use multiple nodes and they can work on the same problem simultaneously, concurrently. At the same time, when you are doing some kind of reading a file, writing a file, once again, there is a substantial amount of throughput which goes to this attached storage. These are the multiple disks, mostly SSDs, very complicated, very complex software layer to make this efficient and reliable. Okay, so now I believe that when we have this kind of architectural design, we can start talking what it really is right now, high performance computing, and what is high throughput computing. So what is pure HPC? HPC stands for high performance computing, and everybody agrees for this definition, which is on your slide, that this is basically we are basically using multiple nodes, multiple, not only cores, but multiple nodes to solve very complex simulations, very complex numerical problems. So in order to do that, there is a needed additional software layer, which is called message passing interface. Message passing interface allows you to communicate between different nodes within a cluster. On the other hand, HTC, which started to be quite popular recently within HPC environment, is called high throughput computing. And high throughput computing is basically I have a lot of computation which I can do on my laptop, but the amount of this computation and time needed to do so will basically go in a linear fashion. If I have multiple nodes, multiple cores, multiple resources, I can basically start immediately not one, but 1,000 jobs. If the jobs are short, I can submit 10,000 jobs. And depending on the scheduler, which we'll be talking about later on, this can basically speed up your research. And at that moment, I would like simply to ask a quick question. If you can do this in a chat, who identifies himself or herself as an HPC person or HTC person? This would be nice to see what is the spread. Okay. I know the Bernadette you said me, but now is it HPC or is it HTC? Okay, I don't know how to do that. Maybe basically you can unmute and basically say. Okay, so HTC is Bernadette is HTC. That's what I suppose that right now, if this will be the case. However, in essence, both approaches, they don't differ, because these new systems which we've deployed within an alliance recently, they have a single node when has 192 cores, computational cores. So it's really this boundary between HPC and HTC is starting to blur, right? There is quite just a handful of computation which can scale to over 1,000 cores of more than let's say 10,000 cores, right? But they're still around. Definitely, they are still around. They still will be needed. However, much of the workflow can basically right now feed up with a single node. Okay, hold a moment. Sorry. Okay, so right now let's talk about the storage. Typically, when you are getting access to this computational resources, you have four areas you can work with. Whenever you're logged in, you are always put in your home. This is your private space where you can store your code, when you can store your thesis, when you can store your articles you are working on, where you can store your process data, your code, your software, and that's only yours. Only you have access to this data, and this file system, this space which is called home and devoted for you, typically has a kind of a limited capacity, which is called quota. And this quota is in terms of the disk usage, so disk space, as well as the number of files you can store there. Okay. Project is, as the name suggests, is dedicated to your collaboration. So if you are collaborating with someone, you are putting your data in project. Nearline is basically a kind of a cold storage for preservation. It's mostly the type of tape-based. So that's a long time preservation of the data, which should go to the nearline. And most of your stuff when we are computing, when there is a rapid read, rapid write, you are using a Scratch file system. Now, home, project, and nearline are reliable, they are resilient, and they are backed up. So we always have a copy of your data which is in home, and we always have a copy of the data which is in the project. We always have some recovery mechanism for the nearline. As far as the Scratch file system is concerned, it's a very dynamic because we are interested in high performance, high throughput, efficiency. The Scratch file system is not being backed up. So if you erase something from Scratch, this is gone forever. So be careful, keep your data intact, but at the same time, don't rely on Scratch as a file system when you can store your important data. So as soon as you compute and you have processed the data, you should basically archive them and move them either to home, either to project or nearline. Scratch is very, very dynamic. So that's storage, right? Now, with how we are dealing with the software, right? You are computing, you have, you would like to run some simulations, you would like to run some computations, and you need some software to that. So on every system with an alliance or UBC, you can always install your own system. If you're sharing this software, you can install this in a project. If this is only for you, you can install this in home. However, we as the UBC and we as an alliance, we also provide a very sophisticated and quite extensive software layer. And in order to navigate with this software layer, we are using something which is called module system. And I will be talking about this module command in a moment. Okay, just give me a second. So the module command is basically built sequentially and within some hierarchy. So the first modules which are installed are basically totally independent programs which don't depend on anything. The other one is when you are building your own software, you need access to some compilers, interpreters. So then there is another layer of the modules which basically gives you the access to the compilers. Different version of Python, different version of GCC or G4, different version of Intel compiler, different version of NVIDIA compilers. So depending what you need, you either use the modules from the independent program, compilers, and then of course there are compiler-dependent programs. Let's say Gaussian, which is a computational electronic structural computation within chemistry, they insist that it should be used, that their compiler of choice is either Intel or NVIDIA compilers, right? So if you are looking for some specific software, you have to first look for the compilers which were they built with, and then you can load this compiler-dependent programs. The next layer is MPI implementation. If you are developing your own MPI code, or you rely on some programs which are built using the MPI, message passing interface, you have to load appropriate MPI modules. Once again, within Compute Canada, Alliance and Sockeye, we have this MPI implementation built with most of modern compilers. So we have MPI implementation built with the GCC. We have Open MPI implementation built with Intel. We have MPI implementation built with the NVIDIA compilers. So depending what you need, you have to basically navigate with that. And you have to be consistent, right? So if I am interested, let's say, in GROMACS, which is once again molecular dynamics simulations using chemistry, GROMACS typically is built with the GCC, okay? That's the compiler of choice. And it needs MPI layer as well. So yes, you load GROMACS, but before loading GROMACS, you will load appropriate GCC compiler and appropriate Open MPI or other MPI implementation, which was used to build GROMACS. Most of the stuff most of the stuff is basically built quite nicely. There is quite good documentation about that. So read the pages about how to use the command module. Once again, if you build your own software, you can create a module for that. And this module command, module load, module purge, and etc., will be very useful within your job submission scripts, which we will be talking in a few minutes. So right now, okay, we know how to navigate within the storage, where we should store. We already know what software is being installed. Now, how do I interact with the system? When you are working on your desktop or you are working on your laptop, it's simple. You just basically start your computation. However, since this computational resources which we are offering to you, this is a shared resource. We will be talking about the best practices later on as well. So everything within the system is basically shared with multiple users, multiple personalities. We need another layer basically to grab all these different workflows and schedule them appropriately on the system to make the system agile, efficient, and fair for everybody. And most of the HP systems right now within the Alliance, sorry, within Alliance and within UBC, we are all using system which is called Slurm. Okay, this is a resource manager and a scheduler. Slurm talks to all the nodes, finds the appropriate resources for you, and schedules your computations. And we all basically work with the Verscher algorithm. In order to submit a job, you need a job script, which we will be talking about right now. And so the job script is typically a shell script. Okay, so the first line is mandatory. That's basically your shell. You can use Bash, you can use C shell, you can use Z shell. I believe you can also use Python as well. Okay, because Python is interpreted. All of this the first couple of lines, which are starting with the hashbang as batch command, are basically directives to the resource manager and the scheduler what you would like to do. So the most important is you have to estimate how long the computation will run, and you have to ask for the time. And usually the format is hours, minutes, and seconds, separated by the commas. It's a good practice to overestimate slightly your computational time. Since you're sharing resources, sometimes your program can be basically stuck within the I/O. It has to wait for the I/O, or if some other resources are basically used by other jobs running on the same node, so your program can be running slightly slower than you are expecting. So 15–20% overestimation of the wall time is a good practice. But if you are computing for a day, don't ask for 7 days, okay? Because that's too much. The second line is basically saying how many nodes I would like to use for my program. Is it a single node computation, or is it a multiple nodes computation? Then you're specifying the total, either total memory or a memory per CPU in typically megabytes or gigabytes. And of course, then if you're asking for one node, you are asking how many CPUs per node you would like to use, how many cores, right? CPUs per node basically stands for the cores. And then you also have to specify all other options, such as an account, which is mandatory, where your input, where your output goes, where your error messages goes. Would you like to be informed by the scheduler that your program has started or failed or finished? So mail options. Once again, there is a lot of examples how to submit, what are the options, what options to use on our documentation and on the Alliance documentation. And then you are done with this hashbang as batch directives. And then you're basically starting saying in your shell script what you would like to do. So first, load your all modules which your program, which your computations are dependent on. List these modules just to make sure that they have been loaded. And then, of course, we are basically putting some housekeeping, let's say echo host. Here I am asking on which node my job will be running. And then I am starting my computation, specifying some other options if necessary, like input and output, redirections, etc., etc. And then I basically exit when computations are done. Okay, and that's how your typical Slurm job should look like. And now we have the job script. And what is the next? Okay, so as batch command, you're navigating to the directory where you created your job submission script. where you have all your input data necessary for the computation, and basically you do the SBAT, your job. The other commands, just to look at the queue, how many jobs are in the queue. There is an SQ command. If you would like to see the priority of your jobs, the command there is S priority, different options. You can always look at your job using S control, or you can use the set command for the jobs which are already finished to see how they were performing, what was the efficiency, how all the computations went through. And if you would like to first see what is your number of shares, how many shares you have already used, which basically tells you what is your subsequent jobs priority, there is a command as share. All of the systems within UBC and within Alliance, we are using a fair share algorithm to schedule the jobs. In essence, the fair share says that the more you use, the less priority your subsequent job has. At UBC, we basically have only a few increase number of shares for just only young faculty members, people who are just starting. But in essence, all users, all PIs, all accounts are treated exactly the same. Within Alliance, it's slightly different. Every year they have this called resource allocation committee resource allocation call. And depending how do you do within this competition, your number of shares can be substantially higher than the others. However, most of the PIs, most of the users have access to the default number of shares, and this default number of shares typically, for in recent years, basically gives you the ability to use freely around 200 core years per year. Okay, so now let's see, what do you see as a user? So if you see as a user login nodes, you see data transfer nodes, you see the compute nodes, and of course you see these other nodes with the DECMEM, the visualization nodes, open on-demand nodes, and you see that these nodes are communicating with each other, so you see the communication network. However, there is plenty of stuff within the systems which you don't have access to and you don't see them. This is this internal software and hardware, which basically.
Roman, there was a question
I am sorry.
Yeah.
I see. Does the shares value go away over time? Yes, this is correct. The number of shares. So basically, your SS share, this is number of users, and there is this kind of an exponential decay. So if you are computing all the time, the number of shares is growing. However, if you have a break in computing, let's say you are computing today, and then you are not computing for 2 days, after 2 days, there will be a decay of number of shares. So your priority will be definitely higher. Very nice description of fair share algorithm is on our internal UBC webpage. And you can also look at the Slurm documentation. Very nice, clear explanation how does it work, okay? So coming to the back end, what you don't see as a user, you don't see all these admin nodes, all these management nodes. You don't need the nodes which are running this Slurm. You don't need the nodes which are running the data, the globus. So the layer which allows you for the efficient move of the data. You don't see all this computational resources which basically hold together entire file system, which are responsible for the data transfer and the I/O to the disk. You don't need this. You don't see these special nodes which are doing the monitoring of the system, which are doing the provisioning of the computational resources. And you don't see the entire hardware, which basically keeps everything together. You see the communication network, but you don't see the switch or the router, which is basically enabling this. Okay, and this is something which right now system administrators have access to. But in order to make everything working nicely and efficiently, we need to collaborate. Okay, that there is always a possibility that something really bad is happening on the system, and it can be caused by the hardware problem, or sometimes the software issue, or sometimes it's inflicted. It's basically user-based problem. So my pledge here is basically that please don't treat this as your own personal farm of computational resources. You are sharing this, and you are sharing this with your colleagues within your research group. You are sharing this with other researchers within the institution. You are sharing this with other researchers across the country. And you are also working together with all the system administrators who would like to have this system running as smoothly as possible. So that's my pledge to you, that all of that is shared, and the performance of this depends on all of us. Okay, so from our side, from the system administrator sides, we would like to make sure that everything runs smoothly, but very often we rely on your best behavior of the best practices, that you are not causing this problem. Okay, with the hardware problem, we can deal. So what are these best practices in this HPC and HTC environment? Login nodes don't run jobs on the login nodes. Login nodes are dedicated to you logged in, you look at you submit the jobs, you look at your code, you edit your code, you compile your code, but you don't run anything there. Something incredibly short, just a few minutes, 15, 20 minutes test is acceptable. But with this small memory footprint, so basically be as gentle to the login nodes as possible. Very often our login nodes are being swamped because someone else decides, oh, I will run my full-blown simulation right now on the login nodes because it has a lot of memory. There's only a few users at a given moment of time, and such a user starts up a very extensive simulation. Then everybody else who logs in after that see that the system is sluggish. And it's not that the system is sluggish, this is the login node which is sluggish. And that was you who caused the problem. And it will be affecting not only you, but affecting everybody other than you. So these are the best practices for login nodes. Then if you have a lot of data to move around, don't use login nodes. We have dedicated data transfer nodes, which can be used to move the data around. Okay, so use the data transfer node. Whenever you have use computational nodes, use the resources using SBatch, right? Submitting the jobs to the cluster. And again, be considerate. So if I need 5 gigs of memory per core, I will not be asking specifically for the node which has a lot of memory, and I overestimate my memory, because these nodes which have a lot of memory, and there's only a few of them, and they are dedicated for the people who really need this much of memory. Special nodes, again, use the special dedicated nodes for, let's say, interactive work. If I have interactive work, we have interactive queue for you. If you would like to have the visual access to your desktop and use open on-demand nodes, there was a week ago a very nice session given by Jacob, my colleague, which was talking about the open on-demand on Sockeye. And right now, open on-demand is also available on some Alliance systems. And don't stress the this communication network. So please avoid intensive, not intensive, but let's say writing small files or very frequent reads or very frequent writes or reads or very frequent calls to the SQ. If you are monitoring, if your job runs for, let's say, a day, you can check the status of the queue, let's say, every hour. But you don't need to hammer the network and hammer the controller for the Slurm, asking every 5 seconds, is my job running? It will be running. Okay, so this kind of best practices is really, I am asking to be considerate and have them in mind. So as I said, right, that's the login nodes, right? These are the short testing. And when you are doing the data transfer, use Globus. That's a very nice tool and very resilient and very nice throughput. In terms of your computation, when you are doing Scratch, don't leave too much junk behind. Always remove all the temporary files which are not any longer needed. All that kind of hygiene within your data. Now, how to interact with, how to interact with the file system. So, checkpoint here for your jobs. If you are running some kind of simulation and you are doing, let's say you are monitoring how the simulation progresses and you are basically logging, do this with logging outside the main loop. So not every single iteration we are saying, oh, I did the iteration. Do this every 1,000 steps, maybe 10,000 steps, because this extensive logging is usually 1 or 2 lines. Oh, I did this. This is a network operation, right? You are hammering for the file system. You are basically asking all the time over the network, write this line, write this line. And if you are doing this very extensively and very frequently, very often, basically, you are waiting for the right operations to be completed rather than computing. So again, this is good for the debugging and developing your code, but that's what we are doing on this interactive nodes, right? Which are dedicated to that. But when you are doing multiple simulations, let's say you are logging every 10 steps. And when you are running one simulation, it goes bang, 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 no problem, okay? We are doing this nicely. But now imagine that you are not running one simulation, but you're running 1,000 simulations. And all these 1,000 simulations, they are doing this frequent logging. Your space grows much faster than you would like to. And since you are running 1,000 the same kind of simulations and they are doing exactly the same kind of I/O operation, you are basically slowing the entire file system for not only you, but for everybody else. Now, if within Scratch, typically Scratch right now is based, that's a Lustre-based file system, and unfortunately, it doesn't deal very well with the small files. Okay, so if you are doing the small files and you have plenty of them, move your simulations to the local disk. So use this directive slurm tmpg, and all the small files put there on a node. This is typically SSD drive, so it's very fast. You don't have this limitations of number of files. The quota is almost unlimited on a local disk. And the I/O is much, much faster because you are not using the network. Again, Slurm TMPG, if you go to our documentation and look for this directives, you will find this very, very easily. Some clusters, they have a dedicated file system which deals with the small files. So if you need a persistent kind of behavior and you have a lot of small files, basically contact support and ask for the access. Does this system have this kind of a file system which I can use? Please give me access to it. So contact us, right? Overall pledge. There is no bad or stupid or easy questions. Don't be ashamed. Always ask. It's better to ask something very simple rather than later on cause some problems. Okay. Interactions with the software. So yes, use basically module utility, list your modules in the job script, be consistent. So load the modules in a proper hierarchy. So you don't have any conflicts, everything is nice and clean. And whenever you are starting to work on your job submission script, start with the fresh environment, because if you load some modules and then you have in a job script you are loading another modules, there can be a conflict because Slurm job inherits your environment when you are submitting the job. Okay, so always start fresh, use module purge, and then start loading the proper modules. How to interact with the scheduler. I was talking about this querying frequency of the scheduler. If your job is running for an hour, ask if your job is running every 15 minutes. Don't ask every second. Be considering of how many jobs you are submitting to the queue. Since this is a shared resources, yes, I understand that you need to run 10,000 jobs, but 10,000 jobs, let's say on Sockeye, they will be not running concurrently. So start with the smaller number, start with the 1,000 jobs. The bigger the queue, the more time the scheduler needs to process this queue and decide which jobs is running, which jobs is not running. So number of jobs in the queue, your wall time. Overestimate your wall time, but don't exaggerate. If you are using this HPC environment, you have the same kind of simulations, which basically are running exactly the same program. The only input data is slightly different, right? We are doing a sweep across some phase space sampling. Look at utilizing the job arrays. Very nice documentation, how to tie the job array index to your input data, this kind of an approach. So job arrays for the HPC kind of a workflow is definitely a way to go. For other jobs, look at the job dependencies. So you can always submit your first job and then say, okay, I am submitting the other job, and this other job depends on the successful completion of the second one. So job dependencies are also a good practice within HPC and HTC environment. Okie doke. So right now, and this is the example of typical high-throughput computational job script. Again, bin bash directives. Please take a look. I am asking for one single node, because that's typically what will happen in the HTC environment. On the other hand, in the HPC job, I am asking for the multiple nodes. Okay? Because back then, for the HPC job, since I'm asking for the multiple jobs, I have to make sure that my program is MPI aware, that the modules which I load a appropriate open MPI implementation for my job. And I start my HPC job using MPI exec or either SRAM or MPI exec or MPI RAM. Okay. And of course, there is another kind of approach when you can combine your MPI or your message passing interface job with multi-threading. So that's a hybrid open MPI, open MP type of the job. And then again, be consistent. You're asking for multiple nodes. You are saying how many MPI processes I would like to start per node. And as you see, this is the option n task per node equal 1. This basically tells me, tells the scheduler that I would like to start one MPI program per node. And then I am asking how many CPUs per this MPI job I would like to spawn using multi-threading. And here the best practice is to basically using the full node. If you are using a full node for your open MPI or your hybrid computations, you are making sure that you are not sharing this resources within some other jobs. It will be getting a little bit more complicated right now because these nodes will have more and more cores per node, but still try to be as compact as possible. Okay, I believe that's everything which I have to say for today. We really appreciate your input. So my kind request to you is don't be shy. If you have any questions, you can drop by to our office. We are located at the West Mall Annex. We can always connect via Teams, Zoom, email, or in person. Whatever issues you have, ARC support at ubc.ca, that's the place to fire the initial email. And thanks so much. Let's stay in touch. Let's talk. Let's compute. And now I will be ready to, if there are any questions, to answer them.
I also posted some upcoming training. So Roman mentioned some bash scripting in his course. So we actually have an upcoming introduction to bash command line interface training on November 5th, and also introduction to Globus training on October 23rd, if you want to learn more about those two things.
And now, how do I stop the share in the recording right now? How do I do that? Okay. Okay, that's recording. Stop, correct? Where is the recording? Okay.
Thank you so much, everyone, for joining the session. We will be sending you a post-session survey after this, and also the deck with you. So if you have any questions, feel free to reply to the email, and we'll definitely, and Roman and myself will be more than happy to answer any questions that you may have.
Guys, thanks so much. Thank you. Bye-bye.
Bye-bye.
Now, Rachel, tell me, how do I stop recording?
I think I started recording, so let me see if I could stop the recording here. I can't do that. Roman, could you just end the meeting and see if that stops the recording?
Where to do that?
Usually we have a button there, right? But it's not showing up right now.
Okay, recording. Pause recording.